Just take 1 minute, let the recording start. Yeah, go ahead.
All right. So
okay. We at SEDS KCT are very happy in presenting this event, which is Kosmorena' 2021. SEDS VIT is a chapter of SEDS India from Belur Institute of Technology. It seeks to promote space education and provide opportunities for students. The chapter consists of 3 branches: core, outreach, and projects. SEDS VIT projects have greater impacts, in which the well-known drone project team of SEDS VIT is Team Ardra, the aviation team of SEDS VIT project. It is a group of technical enthusiastic students working together to design and create UAVs that are built tough and work smarter. They have put in the most dedicated work to build unmanned aerial vehicles. So now they are here to explain the design of autonomous drones. It's an honor in welcoming you, and I request you to share your experience.
yeah, thank you for that introduction. And good afternoon to everyone, and welcome to our webinar on autonomous drone design. So I'm Adit Kirtani, the captain of Team Ardra, and I've been working in Team Ardra for almost 2 years now, and I've learned a lot in my time, from working on the electrical aspect of drones to even building my own quadcopter and flying it around. So I hope to share some of my knowledge with all of you today and hopefully get more people interested in drone technology. So today we'll be walking you guys through the basics of working on drones. So as you can see on the slide, we'd like to introduce all of you to aerial systems, the concepts behind the working of a drone and also building a drone. And to wrap it up, we'll take a look at the engineering choices scientists have to make while flying and while working on aerial vehicles which fly on other planets. So a bit about us in Team Ardra before we begin. So we are the UAV team of SEDS VIT projects, and we've been working with drones and other unmanned aerial vehicles for several years now, participating in international competitions along the way. While we initially used to work on fixed wings, we shifted to multi-copter systems. So a little video of us flying our drone. Oh, looks like it's not working. Unfortunate. Anyways, we'll move on. Yeah, so some of our achievements in the past. Before we worked on drones, we participated in the Hyperloop pod competition. And after that, we used to work on CanSats. We came second in the CanSat design. And after that is when we started working on multicopters and drones specifically. So we started participating in SWAS in 2018. And after that, we went for Srishti and we came second. And since we've all been working online the past year, we participated in IPAS and we were in the top 50. All right, so now on to the session. So I'd like to begin by describing the various kinds of aerial systems we can encounter when working in this field. So today's session will be geared towards drones, or more specifically multi-copter systems. It's always beneficial to know about the other kinds of systems which exist. So I'll be enabling Q&A for this session. So at the top of my PPT, you guys will be able to see a link. So if you guys have any questions, feel free to send your questions there. So this way I can see your questions and I don't have to switch tabs to Microsoft Teams. All right, so without any further ado, let's begin. So the first kind of drone design I'd like to talk about are fixed wings. So fixed wings are simple designs. They're radio-controlled airplanes, which are very fun to fly. A motor is used to generate speed, and that pushes the fixed wing forward, and the wings are used to generate thrust, which causes the airplane to take off. And the direction of a fixed wing can be changed by using flaps on the back of a fixed wing design. Now, there are many variations to this design. For example, you can have motors either in the front of your fixed wing, you can have them at the back. There are some designs which don't even have motors. They can still be controlled, but you need to launch them by yourself, and they're called gliders. Moving on from fixed wing designs, there are multi-copter designs, and this is what we specialize in. So a multi-copter design consists of multiple motors pointing upwards to generate thrust. So just like fixed wings, there are many variations of these designs. I can increase or decrease the number of motors. I could have 8 motors, I could have 4, maybe 3 also. And you can also change the arrangement of the motors. So as you can see in the image on the right, this drone is actually an octocopter since it has 8 motors. But the motors are placed coaxially. So that means the motors are placed on top of each other. Now each one of these decisions we make, they have their own advantages and disadvantages. Alright, so apart from these two kinds of drones which I mentioned earlier, there are hybrid versions too. So if you look at this here, the image on the left, you notice it's a fusion of a fixed wing design along with a multi-copter design. And this is called a VTOL, or a vertical takeoff and landing drone. So they take off and they land like a standard multi-copter drone, but while in air, they can fly like a fixed wing. There are other designs too, like RC helicopters, for example, which are very popular. They're essentially single copter drones, and they use a tail rotor to stabilize themselves in flight. And on the right, this is something I found really interesting. It's an image which looks like a bird, and this is called an ornithopter. So it's a lightweight craft which flies by flapping its wings. So just like this design here, there are many miscellaneous designs you can come up with for fun. All right, so let's start to understand how multi-copter systems work and how we could build one. So let's start with the basics. Let's begin with the frame of a drone. So when we build a drone, we need to understand what we're building the drone for. So someone may want to build a drone to participate in races. Maybe they want to perform acrobatics or stunts in air. Maybe they just want a powerful drone to carry a camera with a gimbal for photography purposes. So each purpose will require a specific frame design. So racing and freestyle drones tend to be smaller, and FPV drones, or first-person view drones, they can vary in size based on the camera being used. And then for larger setups where we use a larger camera and we need a heavy gimbal, we will need more powerful drones with larger frames. So commonly we build either quadcopters, hexacopters, or octocopters. Now their names reflect the number of motors present on the drone. So quad having 4, hexa having 6, and octo having 8. So the main factors you want to consider when choosing from any of these frames is either the drone weight, the battery weight, the payload weight, or the required flight time. So you have to try and balance these 4 parameters, and you have to see which works best for you. So let's look at octocopters. Octocopters offer a serious amount of lift. So because they have 8 motors present on them, this means you can lift a larger payload. But because the number of motors is higher, it means that the battery has to be more powerful and will be more heavier. Additionally, the frame will also be larger, and that increases the weight of the drone. Quadcopters, on the other hand, can be much smaller and much more agile. But again, the decrease in number of motors means the payload they can carry is much less. Individual scale is also something you should consider when you're picking a frame. So if you're not comfortable with your soldering and assembling skills, you should avoid using smaller frames, because what happens is when you're working in smaller and smaller frames, you're packing all the components present on the drone really close to each other. So that means you have to be very confident in your skills to assemble it properly. However, smaller frames do have their advantages. Again, they're unmatched in racing and freestyle applications. And also for newer pilots, smaller frames are more forgiving because they are lighter, so there is less chance of the frame taking damage. If you do end up crashing an octocopter or a large hexacopter frame, you could either damage the entire drone structure or you could damage the props of the motor. So speaking of motors, let's talk about them. The motors are one of the key pieces of hardware in a drone. So for beginners and for our drone application, there are 2 kinds of motors which we consider. there's a brush DC motor and brushless DC motors. And both of them are based on the principle of electromagnetism. So when the motor we supply current or power to the motor, these windings become energized, which create a magnetic field. There are permanent magnets present in the motor, and due to the a repulsive force is created between the two magnetic fields, which leads to a rotation. So what's the difference between these two kinds of motors? So right now I have a animation of a brushed DC motor. So as you can see here, in the brushed DC motor, there's going to be an armature which is rotating, which has coils wound around it. There's a commutator in the middle, which acts as a mechanical switch. We'll talk about this in a few seconds. There are brushes which connect the power supply to the commutator. So what happens is when we supply power to the armature, a magnetic field is created and it begins to rotate. But at a certain point, it's going to stop rotating, and we need to ensure that we change the polarity, the current here in the armature. And that's why we use this commutator. It acts as a mechanical switch. So to ensure the full rotation happens, the commutator there's a small split in between, and across that is where the polarity changes. In a brushless motor, however, the rotor, which is the part of the motor which moves, it's in the center here, it has two permanent magnets around it. These permanent magnets are surrounded by multiple windings. So for this demonstration, there are 3 windings, but in actual brushless or BLDC motors, you notice there are many more windings. So BLDC motors are controlled by something called 3-phase power. So there is a controller, an electronic speed controller, which is connected to the motor, which chooses which windings are active and which ones aren't. And based on that, you can see that it creates magnetic fields around the permanent magnet in the middle, and that results in a rotation. So these motors also have a sensor present in them. So this allows the controller to detect the position of the rotor, and it allows for more precise control. So now that we know about these 2 kinds of motors, which one do we pick for our drone? A brushed or a brushless DC motor? Well, brushless motors are much more popular than brushed motors, and that's because of the fact there aren't actual brushes present. And the reason for that is when you have brushes, they tend to get damaged over time as they wear out from as the commutator is rotating. With the absence of brushes, it also means that brushless motors will be more efficient. There are no sparks present, and the noise produced is also less. So therefore, we always go for BLDC motors, unless we're building really tiny drones. And in such cases, we can see cheaper brushed motors being used. But when we're looking at BLDC motors, how do we compare them? How do we know which one's the best fit for our drone? And that's determined by something known as KV, or the velocity constant. So the velocity constant tells us how much RPM we're going to get out of a motor. So for example, let's say I have a motor with a KV of 2000. Let's say I connect a battery of 10 volts to the motor. And if you simply multiply these 2 numbers, you're going to get the output RPM. So for a KV of 2000 and a supply voltage of 10 volts, we're going to get an RPM of 20,000. And that's really high. And that's because this formula will give you the output RPM when there's no load connected to the motor. Now, no load means that there's no propeller attached to the motor. It's just simply spinning the rotor. If we do attach a propeller, you'll notice that the RPM will decrease sharply. So higher the KV, the higher the velocity constant, the higher the current draw will be of the motor and lower the efficiency. But how do we know which KV range to go for? And that depends on the number of motors on your drone. So quadcopters and tricopters, which are 4 and 3 motors respectively, you need a motor which has a high KV. But as you're working with drones with a larger number of motors present on them, so hexacopters, octocopters, then you can go for motors with a lower KV. because the motors can compensate for each other. So motors with a lower kV, they run at a slower RPM, but that means they can generate more thrust if you use a larger propeller. And motors with a higher kV are more suited for smaller propellers. So this table here is a helpful guide for people working on smaller drones to figure out which propeller and motor combination you should go for when working with a particular frame size. You'll notice something new here, which we haven't discussed yet in this column, the motor size. There are several 4-digit numbers here, but what do these numbers mean? So these numbers simply tell us the diameter and the height of the motor. So the first 2 digits tell you the diameter, and the last 2 digits tell you the height of the motor. All right, let's move on to the propellers. So propellers are what we attach to the motors to generate thrust. And while they may seem like simple components which we can just pick carelessly, I mean, they're just small bits of plastic, aren't they? Well, in fact, there's a lot of stuff we have to consider when choosing propellers. So the first example is the length of the propeller. A longer propeller can generate more thrust than a smaller propeller at the same speed. But it does require the motor which is attached to the propeller to be more powerful because the motor has to provide more torque. However, this doesn't mean that a larger propeller will let your drone fly faster, and that's actually determined by the pitch of a propeller. So what is the pitch or pitch number of a propeller? Well, it's actually the distance the propeller would move in one single rotation if you pushed it into a solid object. Now, to try and understand that better, try to think of the propeller as a screw, which you're trying to push into a block of wood. So the distance the screw would move in one rotation would be the pitch. So as you can see here, the greater the angle of the blades the propeller make, the more distance they would move in one rotation, and thus higher the pitch number. And that applies to drones too. When you have a propeller with a greater pitch number, it means the drone can move a greater distance in one rotation. So something else which affects the thrust of your propeller, thrust output of your propeller, is the surface area of the blade. So greater surface area would mean your propeller generates more thrust, but it also means that the propeller is going to consume, or the motor is going to consume more power. Now, another way to generate more thrust from your propeller is to increase the number of blades you've attached. So as you can see here, there's some, you can get propellers ranging from 2 to 5 blades. But when you increase the number of blades in a propeller, you do increase the weight of a propeller. And that means that because of the more blades, the increased weight will take more time to reach maximum speed. And the additional number of blades mean there'll be more air resistance against the blades. So you will need a more powerful motor if you do increase the number of blades on the propeller. Another thing to consider is the material of the propeller. It's always better to pick a propeller with a lower weight, so something like carbon fiber. These can be very expensive, but they're very efficient because as the less the weight is, the faster the propeller can reach maximum speed. So something that you may or may not know is not all the motors on a drone will rotate in the same direction. And you'll notice here, like for example, let's look at the quadcopter. So you notice that motors 1 and 4 rotate clockwise, while motors 2 and 3 rotate anti-clockwise. And why do we do this? Well, that's because of Newton's third law. So Newton's third law states that every action has an equal and opposite reaction. So that means as our propellers are spinning, we are pushing against air and we're pushing air down to generate thrust for our drone to move upwards. But that means the air is also exerting a force on our propellers. Now, if all our propellers were rotating in the same direction, then that means that force which air exerts on the propeller would slowly build up over time. And that would cause the drone to start rotating. And it would rotate and end up crashing, which is not good. So that's why you have motors, adjacent motors, which rotate in opposite directions, so that if the force which air applies on the propeller is negated. The tricopter is a bit of an exception to this rule, and it has 3 motors and 3 propellers here. But the reason for that is the motor number 1 at the back of a tricopter has a slightly different mechanism, and we're not going to go into that. It'll become a bit too complex. All right, let's talk about batteries. So batteries are what power the drone and all of its components. So these can be the heaviest, the most expensive, and certainly the most dangerous part of your drone. So you should always be careful when dealing with them. So for drones, you can either consider these two kind of batteries. You can either go for lithium-ion batteries or lithium polymer batteries. Both of them have some similarities. They both have very high energy density. Both are rechargeable batteries. They're pretty good positives. But there are several differences between them, which leads us to use mostly lithium polymer or LiPo batteries for drone applications. So as you can see here, lithium-ion cells, they come in metal cases. So this metal cases, it leads to unnecessary weight, which you don't want on your drone. You're trying to minimize the weight of everything so your drone can fly for longer. Additionally, your LiPo batteries are more suited when you have high current applications. So when you have a motor which is going to be drawing 60 or maybe 50 amperes of current, you're going to have to use a LiPo battery. So how do we compare batteries or LiPo batteries? Well, you'll notice I have a table here with 1S, 2S, some voltages written here, and a few terms written here. So this can be a bit complex. So let's go back to our previous image and let's look at this. So I'm not sure if this is too clear to you guys, but I'll just read out the numbers here. So the first thing written here is 3000 mAh. So this is your milliampere hours. So your milliampere hours tells you the capacity of a battery. So you can think of a battery as a water tank. So a water tank stores water like a battery stores energy. And you can think of your milliampere hours as the amount of water the water tank can store. So the higher this milliampere hour number is, the more energy it can store. Below that, there's several numbers written, and I'm going to read those out for you guys. There's 3 cell, 11.1 volts, and 30C. Let's talk about the 30C first. Your C is your C rating. So it tells you how fast your battery can discharge. So again, thinking of your battery as a water tank, if you want to drain your water tank, you're going to attach a pipe to it. Now you can think of your C rating as how thick that pipe is. So the thicker the pipe will be, the faster your water tank is going to drain. So similarly, the higher your C rating, the faster your battery can discharge. So let's come back to this. We've skipped on something called 3 cell and 11.1 volts. So what 3 cell tells you is that in this LiPo battery, that there are 3 cells present. So let's go to this table here. And you'll notice that the 11.1 volts which is mentioned in the battery is here in the 3S column. And every time you see S when you're dealing with batteries, it means that there are some cells placed in series. So when you have a single LiPo cell, it will be denoted as 1S. When you have 2 LiPo cells in series, it will be denoted as 2S. And we've all studied this in physics. When you connect 2 batteries in series, the voltage output of that battery, of the 2 batteries in series, is going to increase. So it'll go from 3.7 volts to 7.4 volts. And similarly, 3S, 4S, 5S, 6S, all of these correspond to that many number of cells in series. Well, you guys might be wondering, why are there 2 rows for voltages? And that's because as we use a LiPo battery or any battery, the voltage is going to drop as it's discharged. So a LiPo cell, when fully charged, is going to be 4.2 volts. You don't want to exceed this because going above that can damage your battery. And if you damage your battery, it can start puffing up. And the moment it starts puffing up, it's not safe to use. You should dispose of it immediately. And as you use your battery, the voltage is going to drop. So you have your nominal voltage, which is 3.7 volts. Fine, you can operate your battery at 3.7 volts. But if there is a minimum voltage which your battery voltage should never drop or go lower than. And for LiPo cells, 3.2 volts is what I would recommend. Don't go below that. You're going to end up damaging your battery, and again it will puff up and you'll have to dispose of it. So always try to keep your battery voltage above 3.5 volts just to be safe. All right. So we've talked about batteries and we've explained how they're connected in series. But sometimes when you want to provide higher current, what you need to do is you need to connect your batteries in parallel. So similarly, how we denote series using S, we denote parallel using P. So you may see 1P, 2P batteries. So that's 2 cells in parallel. You can have 3P, 4P, so on. All right. So earlier we mentioned that brushless DC motors need to be controlled by a controller. So to ensure that it rotates properly. And that's what the ESC does, or the electronic speed controller. So the ESC has a microcontroller present on it, which operates different ICs on the ESC to convert the DC power, which we get from the battery, into 3-phase power for the motor, for the BLDC motor. And it does so by taking inputs from the flight controller. We'll be talking about the flight controller later on. So as the ESCs use 3-phase power, if we switch any of these two connections, we're going to end up changing the direction of rotation of the motor. So for example, let's go back to a previous slide. Yeah, so let's say I've assembled my quadcopter and I connect the battery and I notice that motors 1, 2, and 4 are all rotating clockwise. Well, motor 2 should be rotating anti-clockwise. And the quickest way to fix this is to simply change the connection from the ESC to the motor. So just by changing any two of these, you can change the direction of rotation. And this doesn't harm the motor in any way. All right. So as each ESC has its own microcontroller on it, you can have firmware running on the microcontroller. So some popular example ones are Simon K and BL Heli. So these firmwares are responsible for the smooth operation of the ESC and for the proper handling of the motor. With some ESCs, you can even upgrade the firmware to newer versions. Now, built into these firmwares can be different modes and settings for the ESC. So for example, you can have brake, soft start, and low voltage. So these modes can affect the performance of the motor and change how they function. So for example, the brake setting, which I mentioned, the brake setting makes the motor stop immediately if we lower the throttle. So normally what would happen is if on my remote control, I set the throttle to 0, your motor would slowly start spinning slower and slower until it stops. But if you have your brake setting active, your motor is going to stop immediately the moment you set your throttle to 0. This has a few applications when you are working on gliders. For example, if you want your motors to tuck away into the frame, then you want to stop them rotate. You want to stop their rotation immediately. Another example is the soft start setting. So what soft start does is it starts the motor up slowly. It doesn't immediately go to the speed you set on the controller. So for example, this setting is used in RC helicopters. And the reason for that is in RC helicopters, you can have many cogs and gears in the actual frame. So if you suddenly increase your throttle, then if the motor suddenly starts spinning faster, there is a chance that you're going to damage those cogs and gears, and you'll end up stripping them, and that's going to damage your frame and it could crash. So that's why the soft start setting exists. But however, for using multi-copters, we don't really need to worry about these settings. And something else you can even do with ESCs is you can even program them. So you can use a firmware, some special cables, and software on your laptop or computer. Some ESCs even have a bootloader on them. So that means you can simply connect a USB cable to it and you can modify it. But for beginners, this really isn't necessary. I built a quadcopter and I haven't had to meddle with any of the firmware on the ESC. So something very important we have to do with an ESC is you have to calibrate them. So by default, when you get an ESC from a manufacturer, let's say I ordered one online, and when it just arrives, it's not going to know the full range of the throttle that your transmitter, your controller is going to use. So because of this, it can result in some issues. So let's say, for example, I fly my drone without calibrating the ESC. That means that you're going to have different motors spinning at different speeds. So the drone's not going to function properly and it could crash. And otherwise, because it's not flying properly, you'll end up putting more strain on the motors and you could end up damaging them. Another issue you'll notice is if you don't calibrate it, but you increase your throttle by a very slight amount, then you'll notice that maybe a few of your motors will be spinning, maybe 3 of your motors will be spinning, but your 4th motor won't be spinning. And that's, again, like you can see in the image, that's because the throttle range of the ESC on the left is not matching the throttle range of the transmitter control on the right. So these two images are a before and after of your calibration. So after you've calibrated your ESCs, it's going to match your transmitter, your control throttle range. And that means all your motors will be working in sync. They'll always be at the same speed. All right. So for an example, I've chosen a random ESC from a website to explain the different stats we see when choosing ESCs. So first of all, let's look at the model, and you'll notice that Simon K is written here, Emacs Simon K series ESC. So Simon K is, again, it tells you the firmware which is on the ESC. If you come down here, you'll notice that a weight is specified. So this ESC weighs 63 grams. Weight is very important when comparing ESCs, as you want to use the lightest components on your drone. So it's always useful to know this. You'll see suitable LiPo batteries mentioned here. So it says 2 to 4S. So this means that you can use LiPo batteries which have either 2, 3, or 4 cells in series. All right. So there are two specifications over here, burst current and constant current. Let's talk about these. So when your motor is in operation and it's going to be drawing a certain amount of current from your ESC. Now, if your motor draws a current which is higher than your ESC can handle, you're going to end up damaging the ESC. So that's what your constant current specification is. It tells you the maximum current your ESC can handle for an indefinite period of time. Now, it's not always guaranteed that your motor is going to be drawing a fixed amount of current. Sometimes when you're flying your drone, if you're performing flips or rolls, or you're taking sharp maneuvers, then your motors can have a spike in current draw, or the spike can last for a short period of time, it can last for a very long period of time. So for that, we have this specification called your burst current. So your burst current is the maximum current your ESC can handle for a limited period of time. So let's say usually it's around 30 seconds for ESCs. So this means that this ESC can handle a current from 60 to 80 amperes for 30 seconds and for no longer. And if your motor ends up drawing a higher current than 60 amperes for more than 30 seconds, you're going to end up damaging your ESC. So when choosing an ESC, you should always take into account the current draw of your motor. So for example, with this ESC, if I had a motor which would draw 30 amperes, then, well, this is fine because your constant current is twice of that 30. So this ESC would work for that. But let's say I had a motor which is going to draw 50 amperes, just for an example, then this ESC could work, but there's always a chance that there could be a spike in current and your ESC is spoiled. So you should always choose an ESC which the constant current rating is around 20 amperes more than the current draw of your motor. All right, so some of you may have noticed something called BEC written here. So what is a BEC? Let's talk about that now. So BEC stands for your battery eliminator circuit. So before we see what it does, let's think of why we need one. So on your drone, there are going to be many components which will need a voltage of 5 volts to function properly. So for example, your flight controller, your receiver, if you have any other sensors present on your drone, if you're using servo motors, you cannot connect your battery to those components because let's say, for example, I'm using a 6S battery, which has 6 cells in series. That's going to be supplying around 25, 24 volts, and that's definitely going to damage your components. So we need a way to supply 5-volt power to your components. And using another battery is not feasible because that's going to increase the weight on your drone. So that's where this BEC, or the battery eliminator circuit, comes in. So what this does is it takes the battery voltage and it steps it down to 5 volts for other components to use safely. So there are a few kinds of BECs. There's linear BECs and switching and universal BECs. So linear BECs are the simplest. What they do is they take the battery voltage, they step it down to 5 volts, and they convert the excess power into heat. But as you might imagine, that wastes a lot of energy. Simply converting excess power into heat makes them very inefficient. Switching BECs, or universal BECs as they're known, are a bit more complex. They use switching, they operate by using a switching alternating current to step down the power, and this makes them way more efficient than linear BECs. They barely waste any power. And just a clarification, when you're looking for BECs online, you may find some websites saying universal BECs, you may find websites saying switching BECs, but in the end, both of them are the same. So some speed controllers will already have a battery eliminator circuit in them. So for example, this one here, it says it has a BEC, and you can see its output here. And if we go back to our previous picture of an ESC, you can see this output here, which I skipped over earlier when I was just explaining the ESC. This is actually the output of your battery eliminator circuit. So it supplies a ground connection, a plus 5 volts, and there is a connection for a signal pin, which is basically how your ESC is controlled. However, you don't have to rely on the battery eliminator circuit, which is present in your speed controller. Sometimes when you're using a speed controller which is rated for high current draw, there's a chance that your BEC may not even be included in that. So always check specifications before purchasing. And additionally, you may have different components which require different levels of voltages. So you may need to use separate BECs than the one which your ESC has. All right, so we've talked about how to power the different modules on our drone, but let's talk about how we can control it now. So using the receiver and the transmitter, or RX and TX as they're known, you can control your drone. So this image shows a receiver on the left with some antennas connected, and this is how it receives the input from your transmitter, which is shown here on the right. So on the left, over here on the receiver, you'll notice that there are many pins which you can connect to your flight controller. So that's how the receiver will tell and receive input from your transmitter and tell your drone where it has to go. Your transmitter is essentially a handheld remote. There are 2 sticks present here to control the various movements of the drone. And different transmitter models will have like a varying number of switches present on them. Some will have knobs, and some of them even have on-screen displays. Some of them might not have this, and it makes them a bit harder to use. So transmitters have something called channels. So right now, if you go on Google and you look for transmitters for drones, you're going to find websites saying 6-channel transmitters or 16-channel transmitters. So what does each channel do, and why do we need so many? Well, a channel is used to control a specific function of your drone. So I have an image of an airplane set up here. So you can see the important controls, the yaw, the roll, and the pitch. This will control how your drone will move. And there'll be a 4th control, the throttle, or how that controls the input to your motors, or essentially how fast you want your drone to move. So you can assign the movements of your stick or any of the switches to these channels to control these movements. So for example, let's say with the left stick, I can use the up and down movement to control the throttle of your drone. So if I increase it, my drone will start speeding up and it will be at max throttle. If I set it to 0, my motors will stop moving. Similarly, you can assign the left and right movement of your left stick to your right stick up and down movement to pitch, and your right stick left and right movement to roll. And it's not necessary you have to assign your stick, you have to configure your sticks in this way. Different models like fixed wings and multi-copters will have different settings. So always go with what's recommended for your specific frame. So additionally, you can see that this transmitter here has several switches and knobs. So you can use these to either switch between modes on your drone or to change the behavior of your drone. Otherwise, if you want to activate specific components on your drone, that's what you use these for. Okay, so we have our transmitter and we have a receiver and we have a way to control the drone. But where does all this data go of my stick, of the movement, or what I'm controlling? Where does all that data go? It's not like we can connect our receiver directly to the motors. And that's where the flight controller comes in. So I've already mentioned the word flight controller once or twice in this session, but we'll be talking about it in detail now. So you can think of the flight controller as the brain of your drone. So it takes in the input from your receiver and it converts it into an output which goes to the different motors or the different ESCs. So I have 3 images here and these are slightly different flight controllers. So I'll start with the one on the right here. You'll notice many flight controllers simply look like a printed circuit board. There's nothing too special about them. In the middle here, you can see flight controllers. Some of them look like separate modules. And so the Pixoc, this is a good example of that. You even have your APM flight controller, and it looks like a separate module which you will place onto your drone. And on the left here, this is something a bit unique. This is called a stack. So what happens is when you're working on really small drones, the amount of space you have for all your components is limited. So what engineers decided to do was to combine the flight controller, which is the layer in the middle, with your ESCs, which is the layer at the bottom. So by combining them two and stacking it, you take less space for both of these components. And if you're using a camera on your drone, you can use the third layer for your video transmission. And flight controllers themselves, they have several sensors present on them, so they can sort of feel how the drone is moving and react accordingly to that. So they can use accelerometers, gyros, they can use GPS data, they can even use LiDAR data. So this makes them very powerful and helps them smooth out the drone's movements. So each flight controller has different flight modes. So a flight mode defines how the drone is going to move and respond to your commands. So for example, we have a mode called Acro, which allows the drone to control every movement of which allows the user to control every movement of the drone without any help from the flight controller. So this is generally used when the pilot wants to perform stunts or tricks with the drone. They don't want the flight controller interfering. So for example, let's say I'm trying to make my drone do a flip, but halfway through my flight controller panics and tries to make my drone level again. And that's going to cause issues. Your drone could crash because of that. So that's why this Acro mode exists. Another good example is the self-level mode. So this is very helpful for beginners, as when the drone is set or when your flight controller is set to self-level mode, it's going to assist the pilot in keeping the drone level whenever they're flying it. So this will make it easier for the pilot to learn how the actual movements of the drone and make it easier for them to fly. So when our drone is flying around, the vibrations from the motors, as the motors are spinning, the vibrations on the motors can reach the sensors present on the flight controller. And this will create a noise in the reading of the sensors, and this will lead to errors. So as the vibration error builds up over time, This can cause the drone to fly around erratically, and it could lead the drone to crash entirely. Otherwise, your flight controller will try to overcompensate for these errors because of the vibration, and that will lead to more strain being put on your motors, and you could burn out your motors. So that's why your flight controller has to be mounted on anti-vibrational screws or anti-vibrational boards or mounts, which exist for bigger models. So what these do is they ensure that the data which the sensors collect is accurate and is not disturbed by the motors. Now, something you may notice when looking for flight controllers are terms like PID or PI controllers. So PID stands for proportional, integral, and derivative, and it's used to control the drone while it's flying. It affects the drone's movements and how it responds to your control. Now, I'm not going to go into too much detail about this topic because explaining it can get very complex, but I will mention that the P term stands for proportional, I stands for integral, and D stands for derivative. And you have to assign a value to each one of these terms to control how your drone responds to your inputs. And you have to find the correct values for your P, I, and D terms to ensure that your drone flies smoothly. And this process of finding the right values is called tuning the flight controller. If you do set your values, let's say you set your P term too high, you can have your drone moving very sharply, like your inputs will be amplified by a large amount. If your I term is too high, your drone can start oscillating violently after some time. So you have to be sure that you're using the right values. All right, so throughout this entire session, we've been discussing how to manually fly the drone. But what if I wanted to make the drone fly itself, if I wanted to make it autonomous? And that's where the autopilot comes in. So an autopilot is a firmware which we can flash onto our flight controllers. So it can do the job of piloting the drone for us. So there are a few autopilot softwares which I just wanted to mention today in this session because they're the most relevant ones when working with drones. So we have Betaflight, you have iNavFlight, and you have Autopilot. The Betaflight is primarily used for racing quadcopters. It's designed for that, but because of that, it's not good for any other applications. So if you are using a racing quadcopter, stick to Betaflight. iNavFlight, on the other hand, is very good with fixed wings and good with drones too. And it works very well with the GPS, but it's not good at handling racing quadcopters. That's the difference between Betaflight and iNavFlight. Autopilot, on the other hand, it's an open source firmware. So it's designed specifically for Pixhawk controllers, but it does support other flight controllers too. And because it's open source, there's an entire community working behind Autopilot, adding new features to it. And because of that, it supports a lot more hardware models than other autopilots would. And it also works really well in all kinds of systems. So for example, you can so there are different variations of Autopilot. You can use Autopilot on drones. There is Arduplane for fixed wings. And you can even put this Autopilot on rovers and submarines and even on balancing pods. So you can see it's really versatile compared to these two autopilots. All right, so let's talk about ground control stations. So a ground control station is a software which lets us interface with the drone. So using softwares like these, it allows us to store a series of positions and behaviors on the drone and onto the flight controller of the drone. And using these softwares, you can plan out entire missions and store them on your drone for your drone to execute autonomously. So on the left here, I have something called Mission Planner, and on the right, I have Q Ground Control. These two are very popular, and you can try out any one of these. When you're using ground control station at a beginner's level, these softwares you can simply click and place waypoints. You can drag them around. You can change the altitude at which the waypoint is located. And you can upload this mission onto your flight controller and your drone is going to execute that. However, there are more advanced features for users who are a bit more proficient with these softwares. So you can use ground control stations to make your drone survey entire areas. You can use these softwares to automatically create paths if you want to map out an area using a drone. Another useful advanced feature, which is demoed here on the right, is called a geofence. So what a geofence does is it defines a virtual fence which your drone cannot go outside of. So this is very useful if you want to limit your drone to a particular area for testing. Maybe you don't want it trespassing in other people's properties. So these softwares have many features hidden in them, and I'd really recommend you guys to try them out. And don't worry if you don't have a drone. You can even try out simulations in these. So there's something called SITL, or software in the loop. So which is something, it allows you to simulate a drone flight. So it's really interesting, and I'd recommend everyone to try it out. So we have our ground control station on our laptop or our computer, and we have our drone flying around. But how do we connect these two? And that is the job of the telemetry module. So it's used for communication between the drone and the ground control software. You can try to think of it as a virtual USB cable or a wireless USB cable, allowing for the drone to communicate and for the drone to send packets of data to the ground control station, and it will allow the ground control station to monitor the movements of the drone. So with a telemetry setup, you can see details about the drone's current flight on the ground control station. So for example, you can see altitude, the orientation of the drone, the speed it's moving at, the current flight mode it's in. You can even update flight modes, and you can make the drone perform interesting acts. So for example, I could go to the ground control station, I could click anywhere on the map, and I could have the drone fly over there. So having a telemetry setup is really powerful. Otherwise, another thing I could do is if I'm done with flying my drone for the day, I could click on return to launch, and that will make my drone come back to where it launched from and land again. So the telemetry communicates with the drone using communication protocols, and one example of a communication protocol is Mavlink. Mavlink is very powerful, and you can use it to even program the drone to act the way you want it to. So using softwares like DroneKit or Mavros, it really unlocks another realm of possibilities with drone technologies. If you do go on YouTube, you can find videos of people programming their drone to follow them as they're moving around. All right, so since Space Week is going on, we thought we'd talk a bit about extraterrestrial flight and the kind of decisions an engineer or a scientist would have to make when changing the kind of models we've discussed, like fixed wing or helicopters or multi-copters, and how to adapt them for extraterrestrial flight. So, well, we all know about Ingenuity. It's the most popular, the only powered helicopter on Mars right now, and it's definitely trending everywhere. So Mars has several conditions which makes it very difficult to fly on. So for example, the Martian atmosphere, it's 0.6% of Earth's atmosphere. That makes it very difficult for us to generate thrust. There are fluctuating temperatures on the surface of Mars. So that will damage your battery and will affect its lifetime. And there is one advantage to flying on Mars, and that is that the gravity on Mars is 38% of our gravity on Earth. So before we talk about Ingenuity and the decisions they made at NASA to make the Ingenuity helicopter fly, we'll talk about the different designs we've discussed in the session and see whether they would work or whether they wouldn't work on Mars. So first we talked about fixed wings. So could we use fixed wing on Mars? Well, the thing is, with a fixed wing, you're going to need a flat area for the fixed wing drone to take off from. And the Martian surface is not going to have anything like that. And additionally, because the atmosphere it's not dense, it's 0.6%. That means that your fixed wing needs to be moving at a really high speed for the wings to generate any amount of thrust. And let's say even if it does take off, when it's moving in air, if you want your fixed wing to make a turn, the turning radius is going to be huge. And so that's why fixed wings can be problematic. Well, if generating thrust is a problem, why not we use a multi-copter? Why not use a quadcopter or an octocopter? More motors should be more thrust, right? Well, the thing is, because the atmosphere is so thin there, that for your motors to generate any thrust, your propellers have to be really large. So if I try to use an octocopter, the size the frame would have to be to accommodate these large propellers would be huge. And that's something NASA couldn't do since the Ingenuity helicopter was sent alongside Perseverance, the Perseverance rover. And additionally, when we're adding more motors on your frame, uh, your frame will have to be larger. That means your entire craft is heavier. Plus, you have to power more motors. And since your battery lifetime is going to be really low on Mars, so again, that is not feasible. So that's why NASA went with a helicopter style design. And they made some really interesting choices. So these propellers are huge, but even though they're really big, they're really, really light too. The propellers only weigh 35 grams. And so they've tried to reduce the weight of the entire craft. And by reducing the weight, it means less thrust is needed to lift the entire craft. So the entire craft weighs less than 1.8 kilograms, and you just have two propellers of combined weight of 70 grams lifting that. It's really marvelous to think about. Then another thing which they did was they made the blade spin really, really fast. So these propellers will spin at around 2500 RPM, which is 5 times the speed which a helicopter on Earth would have to spin at. And they have to be careful with the speed. The speed can't go too high, because if the tip of your blades of the propeller starts reaching the speed of sound, it's going to have some interesting aerodynamic effects, and it's going to harm your drone. So they had to limit the speed, but they had to come up with a suitable design so that your entire craft could be lifted. And to take care of the battery, they've insulated the entire structure, and they have a solar panel on top so your battery can be charged during the Martian day. And they did design the entire vehicle to fly for 90 seconds or less. So that way your battery doesn't have to be too heavy, it doesn't have to supply more energy for a longer flight time. Well, something interesting they had to do was to test the helicopter. And how do you really test something which is meant to fly on another planet? So in their jet propulsion laboratory, they have something called the 25-foot space simulator. So it allows them to simulate any kind of environment or any kind of atmosphere, to be more precise. So, all right, they can simulate the atmosphere, but how do they simulate the effects of lower gravity? So for that, what they've done is they've actually attached a fishing reel, and they've used a sensor and a motor to detect the movement of the drone, and based on that to compensate, to reduce the weight. And that's how they test for the gravity. So I'm just going to play a small segment of the testing. It's really interesting to see. Right. So as you can see, the different parts of the mission which is executing is shown here on the left, and you can see how it functions, how it flies. I'm not sure if the cable is too visible, but it is present over here on top to simulate less gravity. All right. So I hope you guys enjoyed the session, and hope you guys learned something today. Hope you found it really interesting. Thank you for listening, everyone. And you guys, if you want to reach out for further questions, you can contact me at this email, or be sure to follow us on Instagram to see the work we do. I have a question from someone who's asking about the flight time of drones. There's no fixed flight time. It really depends on what kind of drone you build. So, for example, and it also depends on the purpose. So, for the competitions we go for, we need a drone which will have a flight time of 30, 45 minutes plus. But if you're someone who's building a racing drone, you can try to go for something around 15 to 20 minutes. And if you want to increase the flight time, you'll have to look at your optimal setups. I have a slide here in the previous. It'll show you basically the best setup for choosing your propellers and your drone frame. Yeah. So if you go online, you'll have to refer to something like this, and you'll have to. It's a lot of decisions and it's a lot of experimenting you'll have to do. And there's another question about someone asking about ground control stations. I'd recommend trying out Mission Planner. That's the one I've worked with. All right, if anyone else has any questions, feel free to unmute and ask. Yeah, feel free to ask any questions.
Participants, if you have any question, kindly put it in the chat.
If you want to dispose a puffed lipo, you'll have to find. You have in different cities, you'll have different locations for disposing of electronics. You will have to go dispose them there. And yeah, again, for ground control station softwares, you'll have to I'd recommend Mission Planner. It's the one which I used a lot and I personally really like.
Hello, sir. I'm audible.
Yeah.
Hello, sir.
Yeah, you're audible.
क्या मैं कुछ सवाल हिंदी में पूछ सकता हूँ?
हाँ, पूछ लो.
मेरा ये सवाल था कि अभी ड्रोन सर्विस के लिए यूज हो रहा है, जैसे कि पार्सल डिलीवरी के लिए इस वगैरह के अंदर वो यूज हो रहा है. लेकिन मेरा ये सवाल था कि अगर समझो तूफान आता है, तूफान के बाद वो सब कुछ तबाह हो जाता है, तभी भी क्या
your voice isn't clear. I can't hear you.
के टाइम मतलब कुदरती आफत के बाद यूज हो सकता है क्या?
नहीं
बेसिक कुछ
आवाज क्लियर नहीं आ रही.
यूज करने के लिए, जैसे कि मोबाइल टायर समझो. नाउ क्लियर.
हाँ.
अब आवाज आ रही है ठीक से?
हाँ.
हेलो.
या हेलो.
अभी आवाज आ रही है क्लियर?
हाँ.
हेलो. अब आवाज आ रही है? हेलो.
It's kind of breaking. Could you type your question?
कुदरती आफत आती है, उसके बाद जैसे बना गया तो अभी मोबाइल और सब कुछ डैमेज हो जाते हैं, वो गिर जाते हैं. तभी क्या ड्रोन की मदद से टेम्पररी मोबाइल सर्विस यूज हो सकती है? इस तरह से कुछ सर्विस एक कर सकते हैं?
Tej,
Mobile
your voice
service
is
no?
not clear.
Yeah,
ये
you
करके हाँ
could you
इस
type
तरह
your
से उसके
question?
ऊपर थोड़ा मार्गदर्शन चाहिए था।
Yeah, I'll
और
disable
दूसरा
your
एक सवाल था,
mic.
एक मिनट और
Kindly put it
दूसरा
up
एक
in the
सवाल था कि ये ड्रोन के अंदर जो टेक्नोलॉजी यूज होती है क्या उससे हम लोग उसके कुछ कंपोनेंट को क्यूबसेट इस तरह से के अंदर भी यूज कर सकते हैं अगर पॉसिबल हो तो?
I
Thank you.
mean, I don't know too much about CubeSats, but I'm guessing they might have. It'll be a different setup from drones because drones will be using motors, but you won't be seeing that in CubeSats and all. Okay, and so a budget for like making a beginner drone. If you go online, you can find drone kits. Some of them can be expensive, like around 17K and all. You can go for a budget of around 12K to 15K. That's like the cheapest you can get. If you want to get and it also depends how committed you are. If you want to build a racing drone which is going to last for longer, you can go for a more expensive frame. But yeah, I'd suggest sticking to around 12 to 15K. And someone has asked if you want to build an autonomous drone. I'd suggest finding drone kits online. So they'll have all the components together. And there you'll have to ensure that the flight controller which you pick supports Autopilot Softwares. Yeah, you can. So what you can do on your drone is you can have a onboard computer. So you can have a flight controller and you can have an onboard computer. It's two separate things. So your onboard computer can handle stuff like computer vision and all. And not myself personally, but yes, I have worked with people who have worked on this. And yeah, it depends on size, your carbon fiber frame. All right. Thank you. I hope you enjoyed.
Yeah. So I guess there are no more questions. So shall we end the session?
Yeah.
Yeah, Sheikh.
Sure, no. On behalf of SEDS KCT, the entire crew behind the event and myself extend a hearty vote of thanks to the team Ardra from SEDS VIT and all the audience who graced the event in great numbers. A big thank you for this team for amazing and inspiring session on designing the autonomous drones. We were all inspired by your insights, team. Thank you for spreading this great evening with us. Thank you.